Hello everyone, I am Sandeep Prakash Netalkar and you are watching Sandy's Desk. In this video, we shall talk about the concept of nuclear spin and Larmor precession. As we all know, atoms consist of nucleus and a shell, which is made up of electrons. In the nucleus, there are protons, particles that have positive charge, shown as blue spheres. Another particle which is a constituent of all nucleus, apart from hydrogen, is the neutron, which is electrically neutral, shown as white sphere. These particles are analogous to little planets. Like the Earth, they are constantly turning or spinning around an axis. Or, as one says, they possess a spin. Each proton and neutron has a spin of half. The total spin of the nucleus is taken as a vector combination of protons and neutrons spin. The nucleus carries a positive charge because of the presence of protons. Each nuclear isotope, being composed of a different number of protons and neutrons, will have its own total spin value. Unfortunately, the laws governing the vector addition of nuclear spins are not yet known, so the spin of a particular nucleus cannot be predicted in general. However, the observed spins can be rationalized and some empirical rules have been formulated. Nuclei with both protons and neutrons, even, have zero spin. Nuclei with both protons and neutrons, odd, have integral spin. And, nuclei with odd mass have half-integral spin. Nuclei, for which, nuclear spin, I equals 0, are non-magnetic and don't have magnetic moment. Hence, will not respond to external magnetic field. Only nuclei, with non-zero nuclear spin will respond to the external magnetic field. The nucleus being positively charged, as the nucleus spins, the positive charge naturally spins around with it. And, what is a moving electrical charge? It is an electrical current. Now, you may recall from your physics classes at school, that an electrical current induces or causes a magnetic force, or magnetic field. So, where there is an electric current, there is also a magnetic field. Thus the nucleus has its own magnetic field, and can be seen as a little bar magnet. For example, if we consider hydrogen 1 nuclei, that is, protons, normally all of them are aligned in a random fashion. This, however, changes when they are exposed to a strong external magnetic field. The nuclei, being little magnets, align themselves in the external magnetic field, like a compass needle, in the magnetic field of the Earth. However, there is an important difference. For the compass needle there is only one way to align itself with the magnetic field. For the nuclei, however, there are two. The nuclei may align themselves in the direction of the external field, parallel to it. Or, they may point in the completely opposite direction, anti-parallel. These type of alignments are on different energy levels. The ones aligned with the external field direction are lower in energy, while those aligned against are higher in energy. Naturally, the preferred state of alignment is the one that needs less energy. So, more nuclei are on the lower energy level, parallel to the external magnetic field. A smaller number is on the higher energy level, anti-parallel. The difference in number is, however, very small and depends on the external magnetic field. According to the quantum laws, the magnetic moment vector can be aligned, parallel or anti-parallel, only so that its components are either integral or half-integral, in a reference direction, that is external magnetic field direction, and that vector arrow can never be exactly in the field direction. Thus, whichever energy state a spinning nucleus is in, it will always lie more or less across the field direction, and will therefore be under the influence of a couple, tending to turn it into field direction. Its only response to this force would be precession about the external magnetic field direction. Now, this behavior of the spinning nucleus can be considered analogous to that of a spinning top. The spinning top starts to wobble, or tumble around, when you spin it and leave on the surface. It doesn't, however, fall over. During the precession, the axis of the spinning top circles, forming a cone shape. The nuclei in a strong magnetic field also show this wobbling type of behavior, which is called precession or Larmor precession, named after Joseph Larmor. In reality, this is a very fast movement. For reasons we will learn later, it is important to know how fast the nuclei precess. This speed can be measured as precessional frequency. That is, how many times the nuclei precess per second. This precessional frequency is not constant. It depends on the strength of the magnetic field in which the magnetic nuclei are placed. The stronger the magnetic field, the faster the precessional rate, and the higher the precessional frequency. This precessional frequency can be calculated precisely, using the Larmor equation. Omega naught equals gamma b naught. Omega naught is the precessional frequency in Hertz or megahertz. B naught is the strength of the external magnetic field in Tesla. And gamma is the gyromagnetic ratio. The gyromagnetic ratio of a particular nuclei is the ratio of its magnetic moment to its angular momentum. The gyromagnetic ratio is different for different nuclei. For hydrogen-1 nuclei, the gyromagnetic ratio is 42.5 MHz per Tesla. And for carbon-13 nuclei, the gyromagnetic ratio is 10.7 MHz per Tesla. The Larmor equation, in short, states that the precessional frequency becomes higher when the magnetic field increases. Since the gyromagnetic ratio is different for different nuclei, this means that, at the same external magnetic field applied, the precessional frequency will be different for different nuclei. That is all I had for you in this video. If you found this video interesting and informative, please do like and subscribe to my YouTube channel. Thank you for watching.